So last video we talked about the different terms, right? Firstly the constant, then next the zeros, which are the numerators, and then after which the integrators, right? And then your poles, right? So these are the four terms that I'm talking about. So in this video, we're gonna explicitly explain them individually. So as for the simple gain, so there is three, as you can. I mean there's four things, right? So the first thing is actually the gain. The gain itself is 20 log g. If you remember that equation, if you want to find your gain, you use this equation. If you want to find your phase, you get this equation. So it's gonna be, you're gonna memorize it vividly, and then yeah. So in this case, 20 log k, you can still plot your gain, right? There's no phase angle, so your gain is actually one straight line. Okay, so your k is actually a gain. So 20 log whatever gain you'll get from whatever plot lah. Okay, so integrator wise, so this is very simple. So and you know that the phase angle is actually 0 degrees. The reason is that it's only the real axis. Okay, it's the simple gain is a very pure gain. So pure gain means that it's only gain in the real axis. There's nothing changes in the imaginary axis. So that is all it is. And then integrator 1 over s, right? We also explained it already. So if you're gonna do that, 1 over s, you're gonna have 1 over j omega, right? So let me see. So if you wanna do that, you're gonna have, because you know that if you want to find the phase angle, you're gonna have 20 log g, right? Maybe I use different color like this. Yeah. So as you know that this is actually a denominator, so which is actually a poles in a certain way. So this is actually negative. Whatever poles is actually negative, zeros is positive. So in this case, this poles is actually negative. So we have negative 20 log omega. Omega is simply this term over here. J is simply saying that it's an imaginary axis. It doesn't contributes to whatever thing over here. So please be careful of not including J into the system. Okay, please remember. So to simplify, we can say that x is equals to log omega, right? Simply is because when you're plotting your bode plot is actually plotting against some logarithm scales, not the typical x in this case. So in this case, you're gonna, because everything is in terms of logarithm, this is why you can actually change your frequency, logarithm frequency. You can change to x, so that you can actually plot in terms into the so-called the normal coordinate system. So this is why log omega s is equals to x. So you'll also be using this equation often. So I will recommend you use this, remember this thing, right? And then since this is actually a simple integrator, if you remember, this is actually 1 over s. If it's double integrator, you have 1 over s squared. Triple integrator, you have 1 over s cubed. So in this case, you have a simple integrator which is 1 over s. So 1 over s, you know that imaginary over real, tangent inverse, you would get minus 90 degrees. If you were to remember, this is like for the Nyquist plot. So yeah. So and also that this is actually, as you know, that poles contributes to the negative side. So this is why we have negative 90 degrees. Anything, you can just go back to Nyquist plot and check it out. So in order to draw just to visualize the bode plot of a 1 over s, the gain itself is actually this bode plot minus 20 dB. How do we get this minus 20 dB going down? It's actually from this equation. If you remember, we actually say that the gain, if you want to calculate the gain, you use this formula, and then this is the transfer function, you sub it inside, and then you just rearrange, right? So you rearrange, you already you get minus 20 log omega, right? So and you know that x is equals to log omega, so we just minus 20x. So in this case, minus 20x, hold on, minus 20x is simply, the 20 is actually the constant, right? So whatever x value, okay, you'll get lambda. Okay, anyway, so x is equals to log omega, right? So log omega is actually some decibels, if you remember. So minus 20x times logarithm is actually some decibels per decade for some reasons, like the SI unit. So it's a slope lah. Okay, I think you know what I mean lah. And then for the phase angle, okay, you say that the phase plot is too simple, so it's not shown over here. So I believe it's just one straight line, 90 degrees, minus 90. So in other words, maybe I should show you in a. This is why I open up this thing over here. So you give me a moment. So as you can see, the bode plot is actually the gain is typically the magnitude. Okay, is going down, right? And then the phase is just minus 90 degrees, one straight line down. And as you can see, is in terms of radian per second. So you have to be very careful, which is a different one. So I don't think this is in this thing is not radian per second. I think this is something else. So but nonetheless, their plot is similar. I mean the trend. So with this thing, yeah. So let's continue for. So we are so far cleared away the simple gain k and then the integrator. So now let's talk about the simple lag. Lag means that you have a pole. In this case, pole means that you have a negative, you contribute a negative phase or whatever negative gain. So this is why you always have a minus over there. So likewise, simple lead means that you're gonna lead something, so you're gonna plus, you're gonna gain something. So lag and lead you have to be make known of. So the lag itself is actually 1 over the, so it's actually simply the post lah, right? So to find a gain is this. So what the hell is this, right? You may wonder why this thing suddenly become minus 10 log. Okay, this is actually the same as this one. What you're gonna do is actually to simply bring the multiplication up. So let's say you have minus 10 log, right? So a square, right? So if you were to bring it down, you're gonna have minus 20 log a, right? So this it takes hold of this rule lah, okay? So in this case, when you're gonna like factorize out the 20 over here, I mean the 2, so you have a minus 10 log. You're gonna transfer the 2 because maybe like 2 times 10, right? So you have 20, right? This is times. So now I factorize out the 2, so I bring this 2 over here. So this whole thing will become 1 square plus s omega c, then the whole thing square, right? What the fuck am I doing? Hold on. So I'll have minus 2, right? 10 log 1 plus s, like that, right? This is actually plus, right? This is actually plus. So if I were to bring this dude up here, this is the rule. So I'll have a minus 10 log over there, right? So if I were to bring this in, bring the square in, what I would have is that and then you will get something like that. I don't know where I spent a long time trying to solve all this, because this is simply not the. In fact, if you expand, I believe you will come to here. I don't know, but because they are inside here, so trying to expand this, it's very difficult, right? Because 1 plus something, as you can see, there's an equation over here. Log, let's say base 2, right? A plus b. You have log base 2a plus. Dun dun. What the hell? So it's very hairy, but the concept is there. Alright. So in other words, I think you get what I mean already lah. I just simply factorize out 2 and then I just bring it over here. And then the rest of it is logarithm. Okay, eventually you will get this thing over here. Right? Eventually you will get here. But you just memorize this equation will do. Please, okay? For simple lag. Okay, for simple lag you're gonna do that. For simple lead, you're gonna have this one. Right? So it's for gain for simple lag and lead, you're gonna use 10 log. Right? And as for integrator, you're gonna have 20 log g. Okay, so this is the difference you're gonna take note of. Right? So nonetheless, if you want me to spawn out the answer how to derive this, yeah, I don't know lah, yeah. So let me clean up. Let me repeat again. If you have a simple gain k, okay, if you are a controller and you have an integrator your gain formula is 20 log your transfer function. I mean not I mean your term lah, okay? 20 log k. If it's k, then it's 20 log k. If it's 1 over s, it's 20 log omega, right? So it's minus 20 log. I mean, yeah. So that is 20 in the magnitude, right? But for simple lag and simple lead, okay, you're gonna have 10 log. So this is the very key difference. I just want to, otherwise, yeah. So let's continue over here. So once you have this, there's a few conditions in order to plot the bode plot. And so this term is actually, hold on, this term is actually your corner frequency, okay? This is actually your corner frequency. And then take a look in your IDS is actually your cutoff frequency, okay, where you cut off. So this is the point. So cutoff frequency and your corner frequency, they are actually the same meaning lah, right? They are, buddy. So okay. So in this case, if your corner frequency, I mean your corner frequency is larger than your omega, because this is the the denominator. So let's say this is very big, right? Let's say 1 divided by maybe like 10,000, you're gonna have 0.0000. So eventually you get to 0, right? So this term will become 0. And 1 plus 0 you have 1, right? So minus 10 log 1 is actually equals to 0. So there is 3 conditions for if your corner frequency is larger than your given frequency, okay, then you're gonna have 0 over here, right? So if it's equals, okay, if this dude over here is equals to this one, they'll have this thing will become 1, right? So 1 plus 1 is equals to 2, so we have minus 10 log 2 equals to this value over here, right? So if you have, likewise, if you have a omega that is larger than your corner frequency in this case, okay, if this dude is much larger, you're gonna have a hell lot of gain. I mean in the negative area because you are lagging, so you have a lot of lag. So in this case, this one will dominate. So if this one dominates, under this condition, okay, what you have is this formula. Okay, so how do you get this formula? This is simply also the logarithm rule. Okay, it's a simple logarithm rule, not as like this one. This one is like wow. So 20 log omega c, right? So in this case, what we have is actually let me see, where am I? I should add in this term over here minus. Later you don't know what I mean, because minus 20 log, okay, divided by omega, minus 20 log omega is actually this term, right? Minus 20 log over the omega, the cutoff frequency, is actually this dude over here, right? So in fact, because omega divided by, so in the logarithm rule states that you would have a this thing minus, because this is divide minus, so this is simply like logarithm a over b is equals to log a minus log b, right? So this is actually the a, this is the log a, this is the log b. So this is what I'm talking about. So if you go to minus, this one minus will cancel out, will become plus. This is why you have a 20 log omega c over here, right? And then now you're left with minus 20 log x, 20 log omega. And you know that x is equals to log omega, so therefore it's minus 20x. We have over here this term, right? So with this term, you have another condition, okay? You have another condition, a lot of condition. So at this, because under different condition, you have a different bode plot. This one you have a some bode plot, this one will have another bode plot, this one will have another bode plot. So you need to know which condition you are talking about in order to have which type of bode plot you're gonna bode plot. Okay, so in this case, if you have a omega much larger than your omega c, okay, your corner frequency, you have this equation that governs how your plot will go like. how a plot will be like. And then if your omega is equals to omega c in this case, right? If in this case your omega, okay, and that's because it's this formula. So if this is equals to this, what you have is actually equals to 0, right? You know why? So because as this, let's say this value is 1, and this value is 1, you know that minus 20 log 1 minus minus is gonna plus, right? So plus 20 log 1 you're gonna have, they cancel each other, so it becomes 0 lah. So this is why you have a 0 dB, which is a straight line, which is the gain is actually a straight line, right? So so you may wonder, okay, there's one mistake over here. I say that this is one bode plot, this is one bode plot, this is one bode plot. Okay, this is totally nonsense. Okay, I realize. So if omega c is larger than omega, right? So if omega c is larger than omega, you would have this line over here. Wait, let me see. Yes, you have this line over here, right? This line is actually when your frequency is smaller than your cutoff frequency, you'll always be like this, right? Up till here, omega is equals to your cutoff frequency, or your corner frequency. You start to go down, right? When it's going down, you have a frequency that is larger than your cutoff frequency, right? Because, okay, maybe I should plot it out. As you know, this is actually the frequency graph, frequency and the gain graph, right? Because, yeah, this is the frequency, like x equals to logarithm. Alright, so as the frequency is low, okay, this is lower than your omega c, you're gonna have all the way this straight line over here. Okay, this can be proved by the equation that we derived earlier, states that if your omega c is larger than omega, you have 0, and also when omega is equals to omega c, you have a straight line passing through 0 dB. So in this case, at omega equals to omega c, you have this point over here, which is kind of a little straight line, alright? And then at this point, you have a minus 3 dB correction. The reason why is because you have this thing over here. It's a little complicated, right? So maybe I should. So at this portion over here, you're talking about this line, right? And then if omega is equals to omega c, you're at this point, right, which is a minus 3 dB. You have to write that, right? And then nonetheless, you also have a omega is equals to omega c over here, right? This is when, so in this condition it is just a straight line, but it cannot be seen, so let's ignore that. But nonetheless, if you have a omega frequency that is larger than your cutoff frequency now, okay, this is at this point is omega is equals to omega c, right? So at this line, omega is actually larger than omega c, so you're gonna have a minus log. So you in this case it's a minus dB lah, okay? It's a minus dB per decade, that type of thing. So this is actually a low pass filter. Okay, this is actually a low pass filter if you take note of. A low pass filter in this case is actually a 1 over pole, right? Is your 1 over something is actually a low pass filter. You're gonna filter out all the high pass frequency, as you see that when your frequency is gonna larger than your corner frequency, this is like a limit. So if you're larger than it, you're gonna isolate it. So this dude is gonna become lesser. So in this case, you're gonna minimize this signal over here. So you retain the signal over here when your frequency is equals to your corner frequency. So this is just the meaning of that, right? So the governing equation is simply this one, right? For a simple leg. Okay, so be very careful of what you are doing, right? So likewise for simple leg is the same thing. Okay, the everything is just a flip of it. If you take note, this is actually this thing, right? This is actually the poles, right? 1 over something, the simple leg. So in the other way, this is actually the simple lead. Okay, this is the simple lead. So for the simple lead wise, it's talking about this is actually a high pass frequency, high pass, high pass filter, high pass filter. So you're gonna filter all the low frequency. As you can see, the low frequency is all here. This is in terms of gain. I repeat again, gain versus frequency. So frequency at a low, just below the corner frequency is actually the signal is 0, right? And then after which you're gonna have a increase as your frequency increases. You're gonna have an increase in this manner. So this is just simply the flip of this. This is totally, if you put them together, they will cancel out lah, because they have the same amount of dB, but in the opposite way. 3 dB, that of thing. So this is why I'm not gonna talk about the simple lead, because it's exactly the same as simple light, but in a flip, in a way. So I've cleared out the simple things between simple gain, integrator, simple light, and simple lead. So these four terms are being explicitly defined. I spent a lot of time. I shouldn't do that. So yeah, I'll see you in the next video. We'll do some examples. See you there.